Hello, our project is an FPGA-based implementation of JPEG compression done as part of the ES204 Digital Systems course under the supervision of Joycey ma'am. And our team consists of Jaskirat, me, Nishchay, Romit, and Soham. The aim of our project is to compress a grayscale image using JPEG compression techniques and implement this pipeline on an FPGA. Let's start with the problem statement. We are given a grayscale image of resolution 128 cross 128 pixels with 8 bits per pixel. And our task is to compress this using JPEG compression. Now, how does this even work? So, human vision is very sensitive to brightness as compared to color, and we don't perceive high frequency texture details very well. JPEG compression takes advantage of this and drops less noticeable information to reduce image size. So, to extract the high frequency components in the image, we use the discrete cosine transform, also abbreviated as DCT. As shown in our pipeline, we break the image into several blocks, more precisely 8 cross 8 blocks. And you can see this is the DCT matrix, this is its coefficient, and this is the block itself. And this is the result of this matrix transformation. And then we can also select the most significant coefficients, either the top K cross K matrix or through quantization. So this allows us to significantly reduce the data while retaining most of the image quality.
Let's talk about what is DCT. So DCT is discrete cosine transform and it helps us separate what is important from what is not. For example, we have a 8 cross 8 block image and we want to find its components. Let's consider a 64-dimensional vector space. Each 8 cross 8 block will lie in that vector space. What are the basis vectors for that vector space? So these 64 vectors which you see over here are the basis vectors for that particular vector space. Now every 8 by 8 image block can be represented as a linear combination of these. DCT is the process of computing the coefficients by which we weigh these 64 basis vectors to get our 8 by 8 block. Now, as you can see, the frequency in x direction increases when we go along the x direction in these basis vectors, and same goes for y direction. Now, these are the high frequency components. Our eyes cannot perceive these. So, we can safely neglect these components and then reconstruct the 8 cross 8 image by using the remaining vectors. That's where the compression happens. Suppose for a particular 8 cross 8 block, we get these density coefficients. And there is the standard quantization table. We divide each entry in these density coefficients matrix by this corresponding entry in the quantization. And hence we get the quantized coefficient. As you can see, the high frequency components corresponding entry in quantization table is very high. So these normally tend to become zero. And that's where the compression happens. Now, what is another approach for compression? These were the standard quantization tables. Rather, what we can do is just take the top k by k components of the principal matrix. Let's say I choose k equal to 5. So I just consider a top 5 cross 5 matrix from this 8 cross 8 matrix. And we set all the remaining coefficients to 0. We use this as well as the quantization tables in our demonstration.
So this is the block level overview of our approach. We receive 128 from 128 pixel image. We serialize using Python and send it to our FPGA board in UART. We store it as 8 bits on a VRAM. We do our DCT processing and send it back to our PC as in UART. We receive it as 16-bit values in Q11.5 format. Now, if I plot these, I receive this coefficient matrix and I can reconstruct our image using SciPy. This is my main module, DCT top. After receiving my serial input from IMRX, reads pixels from the DRAM, does DCT processing, and writes it back to DRAM. Another important thing to note is we use a slowdown block everywhere. This is because, again, we can have issues while reading and writing on DRAM. To avoid that, we use a slowdown block. And this is sending back from DRAM to our PC. This module receives serial data and stores it into memory. I have two states, idle and receive. If rxd is equal to 1, I wait in my idle state. If rxd is equal to 0, that is we have received the start bit. After receiving the start bit, I can start reading my data into VRAM. I generate ticks at 4 times my baud rate for oversampling, and at exact center, that is after 2 cycles, I sample it and write it. Similarly, I wait for 10 bits, that is start plus 8 data bits and one stop bit. After that is done, I load it in my VRAM. After compressing the image, the next step is to transmit the data serially from the FPGA. This module reads bytes from the block RAM from a signal called DOUT-TX and sends them one by one through the TXT line. Our FSM starts with the idle state, and if the transmit signal is low, then it stays there in the idle state. But once transmit goes high, we transition into the transmit state. In the transmit state, we first load a byte from the memory into a shift register. Specifically, we have 1 bit followed by our 8-bit data, and then again a 0 bit. And on every clock cycle, the least significant bit of this shift register is sent out via TXT. And after each bit is sent, the register is right shifted and the bit counter is incremented. So once our bit counter reaches 10, meaning all 10 bits have been transmitted, we raise the TXT done flag and we return to the idle state. And we also assert increment address to load the next byte from the memory. Now coming to the main DCT top module, when we signal the process to start using the switch on the FPGA board, we start reading each pixel value and store them in a register. We read the pixel values until we reach the end of the 8 by 8 block. Now we move to the processing phase. We tell the DCT process module to start the matrix multiplication process. Then after the module says that it's done, we wait for the writing phase of the module. While writing, we'll split the values into half because we have 16-bit value and we are storing them in 8-bit VRAM. We store one half of the value in one section and another half in another section of the same DRAM. Now we move on to the next block and this process continues until we are out of the blocks.
Let's see how the DCT process module works. So it is a simple FSM with 4 states as shown here. We take the input as the 8 cross 8 block and it is a flattened 8 cross 8 block. Now we start and there are two multiplications to be done. First is this x first multiplied by the d coefficient matrix to compute dx and we call it interresults. Then once the multiplication 1 is done, we move to multiplication 2 where we transpose v and set v to be d and the a to be interresult. And hence we get dx d transpose. And we return this flattened matrix once we are done. And once we are done, we stay here until we are given with a reset. Now, how does matrix multiplication happens in our implementation? It's a standard row cross column matrix multiplication which we have implemented. So once we have loaded the matrices A and B, then we compute. We check if we have to transpose B, then we just interchange the indices. Suppose we were doing B I comma J, we just do B J comma B. And once the result has been computed, we move to the done state. And if we have to quantize, then we do the quantization process by just a simple arithmetic right shift as we are using powers of two quantization table. And once we are done, we stay at the ready state. Now, one thing to notice that in our implementation, all numbers are 16-bit in Q11.5 format. So once we multiply two Q11.5 format numbers, we get a Q22.10 format number. So our accumulator is 32 bits, 22 plus 10. And we truncate the first 11 bits and the last 5 bits to get 11.5 result. And we have ensured that the first 11 and the last 5 bits are not that significant as the DCT coefficients which we get are in a range of minus 1024 to plus 1024. So that comes well within the range of 11.5. Now, this is the process of matrix multiplication. What we do is we first compute the first row multiplied by the first column, and we store the result in the accumulator, and we sum over all. We use DSP slices for multiplication as they are very fast, and for the entire module, as seen before, slow clock is used so that we give accumulator enough time to accumulate the results, and it handles all the delays of the adders and multipliers.
Now I'll explain the quantization process, which we can optionally perform after calculating the DCT coefficient matrix. We have the standard quantization matrix, which we took from literature, and we rounded off each of the values to the nearest powers of 2 for ease of use. Then we took the log base 2 of each of the values to get the number of shifts required to divide the DCT values with the required amount. Now we use the given formula to shift, which is like division for each of the DCT coefficients values. This process makes sure that we are eliminating the high frequency components of the DCT coefficients, since we are only going to use or will only need the low frequency components. Coming to the FPGA implementation of our project, we have three LEDs which correspond to the three processes we have for the module. These LEDs act as indicators for each of the phase we are in the FSM. The first switch is used to receive the values from Python using UART. The second switch is used to trigger the processing, which is the DCT coefficients processing. And the third switch is used to transmit the calculated values back to the PC using UART. Also, it is necessary to switch off all the other switches while we are switching on one of the switches. Now we can see the hardware utilization reports of our project from the Vivado software. The left image shows the utilization when we do not have the quantization on, and the right one shows the utilization when we switch on the quantizer. We can see that our project utilizes the DSP slices for fast and efficient matrix multiplication. Also, we can notice that once we turn on the quantizer, the number of flip-flops and LUTs go down a bit. On the left, you can see we have our original input image, and to the right, we have our output image, which is a reconstructed image. As you can see, the quality of both images are nearly identical. PSNR value of the output image is 40.55 dB, and this indicates very minimal loss. This is because our DCT coefficients are very accurate, which is a result of us using the Q11.5 format. If we use top K by K principal matrices from our DCT coefficient matrix and we construct our image, we get the following outputs with these PSNR values. Here we can see the reconstructed output images after quantizing the DCT coefficients matrix. This results in a very harsh and blurry reconstruction with the following PSNR value.
Let's see what the compression ratio we have achieved. So we define compression ratio as output bits upon input bits. We have inputted a 8-bit 128 by 128 image. And we have three approaches. One is no quantization, that is, we just compute the DCT and return the coefficients as it is. So the output is 16-bit rather than 8-bit. Hence, the compression ratio is 2, which is not exactly a compression as we have doubled the size. But when we consider top K by K and let's choose K equal to 4, then we achieve a compression ratio of 0.5, which is pretty good. We have half the image size. And once we use quantization in powers of 2, we achieve a compression ratio of 0.78 as roughly 25 coefficients become significant and others are 0. Now, one thing to note is, as you have seen before, quantization in powers of 2 results in a significantly worse images. That's because we have used a very harsh quantization, that is powers of 2. Rather, if we had used the original quantization table, but that would require significant changes to our module, we would have achieved similar compression ratio, but a pretty good visual result. Here is a demonstration video.
This is the implementation video for DCT on FPGA. We have two bit streams to test. One is with quantization and one is without quantization. Let's program the FPGA. First, we are testing without quantization. The FPGA is programmed, and now we run the script which sends the data to FPGA, waits for it to complete DCT, and then receives it back. Now let's flip the switch. The data will be sent to the FPGA. These indices denotes the pixel count. So we have 128 by 128 image, so 16384 pixels, and these are the pixel intensities, and it is a grayscale image. So we have these 8 LEDs over here which depict the data being transmitted. These are 0 to 255 binary numbers. Then over here this LED will light up when the image has been received on the FPGA, like it has been done. When we push this DIP switch, then this LED will denote when the DCT has been computed, and lastly we push this to receive the data. So right now it asks me to flip the DCT switch. So let's start DCT. Over here these LEDs indicate which block is the DCT being processed on, and as you can see, under less than 10 seconds the DCT has been computed. Now let's press enter over here, and after the countdown we will flip the transmit button. The data is being received over from the FPGA. Now it is reconstructing the images which we have from the coefficients which we received from our FPGA, and as you can see, I'll just show you the images. Over here I'll display the images which have been reconstructed using top 3x3, top 4x4, 5x5, 6x6 and 8x8 coefficients. So this is the input image which we sent. These were the DCT coefficients which have been received through the FPGA. Now when we use only the top 3 coefficients, for example over here this particular block, let's say we only use the top 3 coefficients from this block, then we reconstruct the image and we get this with a PSNR of 24.1 dB, and as we increase the top k coefficients, the signal to noise ratio increases. And this is fully reconstructed image, and it has minimal loss. We have a RMSE of 3.70 on the scale from 0 to 55 because of the quantization losses when we represent the DCT coefficients in a fixed Q11.5 format. Now let's move on to the second bit stream. We will refresh our FPGA. Then we will program using detonator.bit. The FPGA has been programmed. This computes the DCT and then divides it by the powers of 2 quantization table. Run the script again to send the image, and you flip the receive switch. The data has been sent and the LED is also lit up. We will do the DCT. And wait for it to start receiving on our laptop. Now one thing to note is that there will be significant distortion in this particular image because we have used a very harsh quantization table. So as you can see, the signal to noise ratio is really poor, as the image has been significantly compressed. And let's see the result. So here was the input image. These were the DCT coefficients which we received from the FPGA, and here is the reconstructed image. As you can see, it has a lot of distortion, but one thing to notice, the distortion is pretty uniform. If I zoom in at a particular patch, we see that there are these particular 3 pixels and a pattern is being repeated, which can be removed in post-processing by a simple convolutional filter. So this was the implementation, and other images can be seen on the GitHub link.